Hi, my name is Jody Sheets, and we're going to be looking at homework from week 3, problem number 10. We're going to look at the solution to that. Problem number 10 says, prove that a graph G is bipartite if and only if every subgraph H of G has an independent set consisting of at least half of the vertices in H. You'll notice in this statement is an if and only if statement, so we're going to be looking at proving this statement to be true, both forward and backward. Before we do that, we're going to look at a definition that is important in this proof, and that definition is of an independent set. It's found on page 63 of our textbook. The definition says, a set of vertices is said to be an independent set if they are pairwise, non-adjacent. In other words, there are no vertices within a set that are adjacent to one another. If that's the case, it's an independent set, contains no adjacent vertices. So now let's first of all look at proving our forward statement to be true. That graph G, if graph G is bipartite, then that implies every subgraph H of G has an independent set consisting of at least half of the vertices of H. So first of all, we're going to look at what the graph G could possibly look like, being a bipartite graph. And if we start with graph G and what we know to be the definition of bipartite, we know that a bipartite graph can be partitioned into two sets. So we're going to call these two sets X and Y, and the vertices, some of the vertices from G are going to be in X and some of them are going to be in Y. So let's say we have X of 1, X of 2, X of 3, down to X sub M. And in Y we're going to have Y sub 1, Y sub 2, Y sub 3, down to Y sub N. And we know that for every edge that is part of graph G, every edge has an end vertex in set X and another end vertex in set Y. So we might look something like this. Okay, and having the other vertices connected in the same manner. But you can see that for all these edges that I've shown, that each of them has an end vertex in X and an end vertex in Y. And seeing this, we can see that the set X has no adjacent vertices, and so by definition we could call it an independent set. And set Y has no adjacent vertices, and by definition we can call it an independent set. So both X and Y are independent sets. Okay? So also let's talk about how many vertices could possibly be in each set. How could we partition the vertices? As long as we keep the requirement that each edge has an end vertex in X and the other end vertex in Y, we can partition the vertices in any number of ways. X could have one vertex and Y have the rest. X could have 2, Y could have the rest. No matter how they're partitioned, one or the other of the two sets is going to contain at least half of the vertices. And so either X or Y will consist of at least half of the vertices in G. Alright, so notice that starting with G to be a bipartite graph, we concluded that G being bipartite has an independent set that contains at least half of the vertices in G. And so what I think we're looking at here is if we can show that every subgraph H of G, if we can show all those subgraphs are bipartite as well, then they can also be partitioned in this manner and have an independent set consisting of at least half of the vertices in G. So let's take a look at how we could possibly come up with the subgraphs of G. Okay, so let H be a subgraph of G. And we're going to break it into sets X prime, such that x prime is the intersection of x and the set H, and y prime is the intersection of the set y and H. And so visually we could see this over here, that x prime might consist of those vertices and y prime might consist of these vertices over here. And you can see that x prime is a subset of x and y prime is a subset of y, and the two of them together make up H, which would be a subgraph of G. Okay, so let's start off. First of all, let's make an assumption. Let's first say assume H is not a valid bipartite partition. Okay, we're going to assume it's not a valid bipartite partition. And in doing so, without loss of generality, we can assume, let's say in set X, that there are two vertices, let's say x of 2 and x of 3, that would be adjacent. Okay, if it's not a valid bipartite partition, if two of the vertices in x prime are adjacent. Well, if they are adjacent in x prime, that means they're adjacent in H. And by definition of a subgraph, if they are adjacent in H, they are also adjacent in G. Alright, well if these two vertices are adjacent in G, then that would make G to be an invalid bipartite partition, which is a contradiction. Okay, so our assumption led to G not being bipartite, which was a contradiction because we started off assuming that it was. So that means that our assumption was incorrect. So we can conclude then that H is a valid bipartite partitioning, and therefore, if all of our subgraphs H are bipartite, then all of those subgraphs are going to contain an independent set which consists of at least half of the vertices in H. Okay? Now we're going to move to the backside proof. And the backside proof looks like this. If every subgraph H of G has an independent set consisting of at least half of the vertices in H, then G is bipartite. And we are going to use the contrapositive to show that this statement is true. While using the contrapositive, this first part of the statement we're going to call P, and the conclusion we're going to call Q. Right? So using the contrapositive, we're going to show that not Q implies not P. Alright? So if we know that not Q implies not P, then we can say that P implies Q is true as well. So we're going to call this statement G is not bipartite. That's our not Q statement. And it's going to apply that there exists a subgraph H of G that does not have an independent set containing at least half of V of H. That is our not P. So we're going to try to show that not Q implies not P. So let's start with G is not bipartite. Okay, according to theorem 1.3, a graph of 2 or more points is bipartite if and only if it does not contain an odd cycle. So according to that theorem, if G is not bipartite, that is going to imply that G does in fact contain an odd cycle. And we're going to call that odd cycle H. Okay, so H is an odd cycle, that just is a subgraph of G. And this is what we're going to define the vertices of H in the following way. They're going to be numbered in order, V sub 1, V sub 2, V sub 3, dot, 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 down to V sub 2k plus 1, because it is of odd cycle, so it has to have an odd number of vertices. And we're going to partition them in such a way that our X set is going to be the vertices V sub I such that I is odd. And our Y set is going to be the vertices V sub I such that I is even. So, our H looks like this. This is our, this is our X set is X sub 1, X sub 3, down to X sub 2k plus 1, and Y over here is going to be our even vertices, V sub 2, V sub 4, down to V sub 2k, and I see that I made a mistake. These should be V's over here instead of X's. My bad. Okay, and we know that since this is a cycle, that V1 is connected to V2, V2 to V3, V4 to V5, and this is going to keep going until finally V of 2k is going to be connected to V of 2k plus 1, and then our last one, V of 2k plus 1, is going to be connected to V of 1 because it's a cycle. It goes back to the beginning vertex. All right, now look at these two sets. X and Y. Well, we notice by definition, X is not an independent set. Okay? It's not independent because it contains a pair of adjacent vertices. Although it contains more than half of the vertices of H, okay? Because it has 1 and it also has 2k plus 1, it's actually going to have more than one more vertice than half. Now over here, set Y, by definition, is independent. No adjacent vertices, but it contains or consists of less than half of the vertices of H. It has one less vertice than this one does, so it has less than half. And what we see here, that this odd cycle H, which is also a subgraph of G, one of its sets is not independent, but it does contain more than half the vertices, and the other is independent, but it doesn't contain half of the vertices. And so what we're looking at is there exists a subgraph that does not have an independent set containing at least half of V sub H. So we have shown that the contrapositive is in fact true. Not Q did imply not P, which means that P implies Q is true. Okay, I'm going back. Okay? And we already had shown that the forward statement is true. And so, because we have shown the forward to be true, the backward to be true, we can say that the statement graph G is bipartite if and only if every subgraph H of G has an independent set consisting of at least half of V sub H. That is also true now because we proved both forward and backward to be true, and that is what we needed to show.